We will come to this module 8, which is basically the sheet metal forming, and today I will start with sheet metal forming introduction. In all industrial processing, you will see that this sheet metal is available in both flat and coiled form in the market. So, either it may be in the coiled form like a big roll, you can see that, or you may get it in different shapes, sizes like 6 feet by 8 feet or 6 feet by 6 feet, like that standard sizes also you may get it in the cut form. But when it is very thin, generally people prefer, and when they wanted to buy in bulk, they buy in big roll form itself, so that it is easy to unwind from that, use it. So, either in flat form or coiled form it is available in the market, and these sheets are basically it is subjected to various processing, sheet metal operations to produce the shapes which you require actually. Okay. And you will see that the type of materials which are available are normally say aluminum, steel, copper, brass, tin, then say materials which are for high temperatures like nickel, or even medium temperatures like titanium, depending upon the use, these it is available. So, most of them commercially available materials are available, aluminum alloys and copper and brass and steel, these are extensively used. Now, in addition to this, there are some metals which are also used for decorative purposes, like with the help of say maybe which are made out of gold or silver or platinum, which are purely for decorative purpose or ornamental purpose. These are also being used. Say steels are extensively used as a sheet metal operation, both for automobile applications and say defense applications, and many other commercial applications. Steels are extensively used. Stainless steels are used even in household purposes, domestic purposes, all these domestic vessels, glass, plates, like that. You will find a variety of things. Most of them domestic application, domestic purpose, it is generally is a 316 or 304 aluminum alloys, but there are other martensitic alloys also, stainless steel also. So, different varieties are there, depending upon, for industrial purpose it is being used. But the stainless steel, the advantages are it is having very high corrosion resistance, hence it is extensively used for domestic purpose. Aluminum alloy is also a widely used sheet metal due to its abundance, cost effectiveness. It is very light and high strength to weight ratio, and it is having a excellent formability, so that it can be easily deformed to any shape without much difficulty. So, that is why aluminum stands on that. And say maybe for the last say 20-25 years, aluminum has picked up in a very heavy way in the domestic sector for most of the case, for kitchen utensils, pressure cookers, and a variety of applications it is being used. Then similarly, brass, which was used right from say maybe for several centuries itself, it is being used as household utensils. Now also there are many clusters at grassroots level in India, where maybe a whole village is making this brass vessels and other things. Okay? And these are also made by from the brass sheets only they are doing, just by hammering on a grassroots level. They do it by just by hammering and getting it into the particular shape. Whereas in industrial purpose, okay, there are some automated machines and other things are, and machines are being done, as well as automation also is there, so that in a large scale these things can be done. So, in sheet metal forming, say for example, when you look at the automobile parts, body parts, then these are all by sheet metal forming. Okay. So, with this today's lecture, I will be referring with respect to the figures which has been reproduced from say Marciniak, Duncan and Hu, the mechanics of sheet metal forming, as well as some part from George Dieter. So that is what. So, many of the pictures have been reproduced also, okay, from these books. So, the sheet metal forming operation, what is it? That means a shape, any shape is which is produced from a flat blank by stretching and or shrinking the dimensions of the volume elements in three principal directions, and then integrating all these elements together. So, you may be sometimes you may be just doing the part by part, and finally, you may just join together to get the final shape, that also is there. Sometimes in single shape, single process itself you will get the final shape, whatever it be. But in this case, it is a sheet metal which you are taking, you are allowing there for some stretching at some places, and or maybe shrinking at some places, and then getting the shape. Sometimes for the final shape you may have to join it also. See, some of the so when you look at a large number of shapes are there, okay. So, it becomes very difficult to put under which category. So, that is a very difficult job, but however, the Sachs has classified sheet metal into 5 major categories. Okay. So, like singly curved part, so that is this part which is there, a very simple shape, a curved shape which you can easily get it. Maybe a sheet metal you can just roll it and get this shape, or pass it through some particular channels and other things, you get the shape. So, these are all this single curved shape. Then contour flanged parts are parts you are going to get it with say maybe the straight flange is there, there should be straight flange. You can have stretch flange, you can have shrink flange. Okay. That means, you are just by bending you are getting a flange part. Okay. So, in a stretch flange, what happens is that the curvature of the bending line is concave and the metal is circumferentially stretched. If you look at this when doing this, it is circumferentially stretched. Initially, the size was maybe like this only before, but after bending there is a stretching taking place, so that you get this this area where A is greater than the B. That is after the stretch flanging operation, you find that this width has increased. That means, it has just stretched that part, that flange part. In this case, the flange undergoes thinning, because when it is stretched, there is going to be a thinning effect to maintain the constant volume relationship. Whereas in shrink flange, it is a different way. There the curvature of the bending line is convex. So, you see that it is convex, and the material is circumferentially compressed into that. So, what was B, this length, has now become as A, where B is greater than A in this case. So, there is going to be a shrinking, the flange undergoes thickening. So, that is the shrinking. But whereas straight flange, you are just bending it, okay, there is no stretching or shrinking, it is the same thing. Then you have say deep recessed part like this, curved sections with the vertical or sloping walls and other things. So, deep recessed part is like say deep drawn cup. So, like this you can get it. Many in the household items you will find these things. Okay. Even industrial purpose also you will see that. Okay. So, either with the vertical or sloping walls, what is shown here is a vertical wall, okay, and then you have the flange here. Then there are the curved sections which are there, maybe like a channel you are getting it curved and other things. So, some part will be stretched, some part may be shrunk and other things. So, those type things will happen to that. So, curved section also is there, and then there are shallow recessed parts like dish shaped or beaded section or embossed or corrugated sections. Even in railways, you will find that many of these things are there. Earlier in toilets and other things, you will get these parts. So, many of the parts in railways you will find that these beaded sections are there. So, the major categories classification he has made is into these 5 parts, and let us look at some of that. But before we proceed further, let us make a distinction between the sheet metal forming and bulk deformation. Say in bulk deformation, you will find that most of the time the material is deformed in all the 3 directions. Okay. So, and most of the case it is by compressive stresses, maybe direct compressive stress or indirect compressive stress. As a result of the reaction, you may get compressive stress. So, any of these things are there. So, normally bulk deformation is carried about by compressive stresses, whereas sheet metal forming is carried out generally in the plane of the sheet, because these are thin sheet, in the plane of the sheet, and they are carried out by tensile forces. Most of the case, there are cases where it is compressive, but a majority of them is by tensile forces. The application of compressive forces in the plane of the sheet may lead to buckling, folding, or wrinkling of the sheet. So, that is also there. If the sheet metal, if you are applying compressive stresses in the plane of the sheet, naturally it will bend, okay, or it may fold off, or it may just, there may be wrinkling, and all those things can happen. So, whereas in bulk forming process, the intention is often to change the thickness or the lateral dimensions of the workpiece, whereas in sheet forming operation, the decrease in thickness is avoided, because all this bulk deformation process, either you have to extend the width or length and other thing and reduce the thickness. Okay. So, for that metal may flow laterally and other things or perpendicular to a direction of your load, which has been compressive stresses. Whereas in the sheet forming process, thickness further reduction is not possible. So, thickness reduction is avoided, because when any process now, when you lead to say thickness reduction, it may result in necking, okay, and then a subsequent failure of that. So, in sheet metal, your aim will be to have the particular shape with more or less the same thickness throughout. That is one thing which people will be looking at it. Another basic difference between bulk forming and sheet forming is that in sheet metal, they have a very high ratio of surface to thickness. That is the one specialty, whereas in bulk forming, the surface area to thickness is very less. Okay. So, let us look at what are these various sheet forming processes. There are a large number of sheet forming processes, some of these only, because if you wanted to write all those things, it will be a very extensive processes, because many of the case, depending upon the need, also people suddenly develop it. So, that way we cannot include all those things, but normal or generally used sheet forming operations, we can say that one is the blanking, bending, stretching, hole extrusion, deep drawing, stamping or rod die forming, tube forming, fluid forming, coining and ironing, roll forming, spinning, and to some extent superplastic forming. Okay. So, let us look one by one. In blanking, this is the first sheet metal working process, because if you are getting it from a coil, in a coiled form, as per your requirement, you have to cut the material as per the size and other things. So, for that this blanking operation is being done. Blanking means there is only a small difference between shearing and piercing. Blanking is the case after cutting, whatever has been removed from the basic form or from the sheet. So, if you are going to use that, then you call it as blanking. That is the only difference. It is only a terminology difference. Okay. So, here you may have to say, even if it is not from coil also, if it is from a standard sheet size, like as I was telling, 6 feet by 6 feet or 6 feet by 8 feet size, standard size is there. From that also you may have to cut the material as per your requirement. Okay. So, for that this blanking operation is used. Okay. And whatever metal is removed from the initial material, raw material, that is that will be the new metal workpiece, which you will be using for subsequent operation. Okay. But this blanking, it is not that easy, it is not that very simple also. You see that it is a complex process. This is the diagram of a blanking operation. There is on this the sheet metal is kept here, and maybe it is held by a block by applying some pressure, and then it is like projecting outside, and a tool just shears it off like this. Okay. So, a tool moves down, causing this failure. So, maybe from this tip the fracture starts, and from here also fracture starts, and maybe it may move like this and then join together, and then you get it separated. So, here the process is very complex, because consisting of plastic shearing and fracture, And when this is happening, when there is a plastic shearing, it may lead to a hardening of the edges. So, when the edge gets hardened and you try to do it in a subsequent operation, because the non-uniform properties will be there, and there it may start forming the defects. That chance is also there. So, you have to optimize it so that it is not getting hardened, basically decided by this the clearance between these two tools. Okay. So, that is one thing, and that depends upon the thickness of your sheet metal. Okay. The clearance will be decided based on the thickness of your sheet metal also. So, that is also there. So, this is a simple blanking operation, this will move here and this will be there. So, this is held there. So, it will just shear off, a very simple operation. Another which is mostly used is the bending operation. Bending is a metal forming of process in which the material bends along a straight line. See, for example, it was a single sheet, but you just kept on bending. So, now you are getting maybe 90 degree or whatever degree you can get it. So, for that purpose. So, in this, during the bending, there is going to be a plastic deformation only at the bend region. Other places there is no plastic deformation. That is why this is shown slightly shaded here. So, at this part plastic deformation is there. So, that part may be slightly work hardened. Okay. So, that it will have a high strength at this region. Okay. So, for this bending operation you need very high ductility. If the ductility is poor, you may not be able to bend it to that much level. Suppose you want a 90 degree, you may not be able to bend it to 90 degree. Okay. So, if the ductility is poor, if the material is brittle, even with a small angle itself, it may crack may develop. So, what is important is that for bending you need to have a high ductility, and so that cracks will not develop during the bending stage. So, bending operations, as I said, I have taken from the book only. These are by different processes, like bending a sheet in a folding machine. So, you are holding this sheet metal here, this is your sheet metal, you are holding it here, and so this is it is being clamped here. So, between two pieces you are just inserting it and then clamped there. That is a mechanical by mechanical means now you are clamping it, and this side also it is clamped, but this is fixed, this is stationary. Here this part you may just rotate it like this up to whatever angle you want. So, this you may just rotate like this, and once it is bent, so it will be rotated about an axis. So, once it is rotated, this part will get bent, okay, and get the shape. But remember, it also depends upon your mechanical properties. If you are just bending by 90 degree, you may not get a 90 degree bend, because there is going to be what is called as a spring back effect. Because of the modulus of elasticity, there is going to be a spring back effect. So, you have to do a little bit of trial and error and find out how much it has to be bent, but then by this machine it becomes very simple. Another easy method is a press brake for bending in a V die. So, this is a V die. So, maybe if you want 60 degree, you can make 60 degree, if you want 90 degree, you can make 90 degree here. In this, you keep the sheet in this V die, and then using a punch you press it, so that finally what will happen, it will come like this. Okay, whatever shape you want, it will come like this. So, the final case it will go like this, you will get the sheet bent. Okay. So, that is that using a V die and a punch arrangement you can do. This is very fast process. Suppose you can also use a roll former. If you want a sheet which is continuously coming and you wanted to bend it, then it is only this, between two rolls you pass it, so that it will get bent when you enter it, and by a sequence a series of these rolls you can get whatever shape you want. Maybe at the first step it may not be there. This is how one of the technique of making this corrugated sheets. So, maybe you can have this rolls, a set of rolls at one place arranged in a way, and then pass the sheet along that rolls and other things, and then you get it corrugated sheets tin sheets and other things which is aware, or galvanized sheets, you will get it. So, that is by this method. So, the advantage is that even if it is a very long process, when you are taking it from a coiled form, you can just have it in a continuous way, and later after this bending operation you cut it. Okay. So, that is one thing, and another is wiping down a flange. Here you are just similar to this, here you are clamping it, and then there is a flanging tool which moves inside this. Okay. So, whatever you wanted a flange to make, so that much the projection will be there, the sheet metal, and then okay, you just pass it through this, because it is clamped here, it will bend and get the shape. So, that is by means of a wiping down a flange. Okay. So, that way you can get it without much of a difficulty. Another is the stretching. The stretching is the forming process, in which, as you see that here in this figure itself, you can see a punch, it is the workpiece is held between, the sheet is held between a die and a blank holder, and then a punch is allowed to move upward or downward depending upon which way you wanted it. Either it is moving upward or downward, so that it will cause this the tensile forces will be generated inside the material, and then it will get the shape change. The inside shape will be decided by the shape of your punch. Okay. So, that way you can get it. So, this tensile forces are generated causing the deformation, plastic deformation also it take place to some extent. Contact stresses between punch and sheet is very low compared to yield strength of the material, that is one thing. Okay. So, contact stresses are not very high. Now, prevent, see, sometimes when you are just it is like a stretching operation, because of the tensile force, the stretching operation is taking place. So, this should be held by very rigidly by means of a blank holder. Okay. So, otherwise what happens is that if there is no blank holder, the buckling of the outer edges will take place when it is, because it is drawn. So, outer edge may get buckling and other things, and you may not get the shape. So, to prevent that, a blank holder is required. Okay. Then only you can have a stretching force. Okay. Tensile forces can be generated and causing the deformation. So, this is much easier to get a simple shapes, axisymmetric shapes and other things. This process is much simpler, and you can get it. Another method is a hole extrusion. You want a hole, but it has to be like extruded part also. Okay. So, in this it is used to first, by you have to pierce a hole. A hole is pierced first, and that size of that first that piercing hole will be less than the final size what you wanted. The diameter will be less than that. So, you first pierce a hole, then you allow a punch to move through that. If you allow a punch to move through this, a punch having a slightly bigger diameter than the piercing hole, the diameter of the hole, then it gets expanded here, and the edge of the hole will stretch. In this case, because the diameter is larger, it will again stretch, but if it is too much, then there may be splitting which may take place. So, one should know about the formability behavior of the material and the ductility, and say other R ratios and other R values and other things you should know. Once you know that, you will be able to tell how much it can stretch and how much this hole can be extruded. If it is too much, there will be cracks. Okay. So, hole will stretch and splitting will limit the height of extrusion. Another sheet metal operation which is extensively used is the deep drawing. Say, if you look at most of the household items, tumblers, glass, steel, glasses and other things, they are made by deep drawing operation. So, with the deep recessed parts, any part is made by deep drawing operation. Basically, a metal blank is radially drawn into a forming die. So, you are going to keep a metal blank here, and it is held by means of a blank holder, and the punch moves down, it moves too much down. So, what happened is that so here it stretches, okay, and then you get that shape. Now, deep drawing is and stamping, though it looks similar. The terminology deep drawing is used when the depth of the drawn part, that means from this here to here, this depth, this h is greater than your blank diameter. H is greater than your diameter. Okay. So, maybe if I say that this is your D, so in this case you call it as deep drawing, but if this depth is less than your diameter, then you call it as stamping operation. That is the only difference. These are processes same, maybe the same machine may be used, but just by this dimension terminology gets changed. So, in order to avoid a flange from buckling, the blank holder is used along with the clamping force. Okay. So, if you do not have this blank holder, naturally you will say it may be drawn inside and you may end up with lots of wrinkles and other things, all those problems will come. So, to avoid that, you need a blank holder which has to be which has to hold the sheet on the die, so that you are going to get this stretching forces on the side walls. Okay. So, in this case the compressive stresses act on this. When you are holding this in this region, you will see that it is compressive forces which are acting, and if you give some good lubrication and other things, it facilitates better sheet movement. In this deep drawing operation, lubricants are generally used, so that it gives a better sheet movement between the die and the blank holder. Otherwise, the even not only here, even in the between the punch and the blank also you should know that. So, these things are there. Okay. Now, when you are drawing, when this deep drawing operation is going on stretching, the metal will slowly move inside also. See, from the blank holder side, it will move radially and then cause that. So, if it is not there, the thickening will take place, but in this case only in a controlled way it will go there and the thickness will remain more or less same. And the sheet metal in this die shoulder region is called as the flange region, which is subjected to radial drawing stress and tangential compressive stress due to material retention. So, it will be drawn inside, metal will just flow into this, it will start flowing into that, and then that will be taken care of by extending the increase in the depth of this. Okay. So, that is what happens. So, radial drawing stresses will be there on this the part in the shoulder area where it is held by the blank holder. Okay. And there are also tangential compressive stresses due to material retention. So, deep drawing is extensively used for getting some specific shapes and other things, deep recessed parts. So, when you look at stamping, there is only one difference. In this case, the depth, the height at which this sidewall movement is there, that is much less compared to the diameter of the punch. So, it is also called as pressing in, which either flat sheet or blank is placed between the punch and the die, and movement of the punch against the die forms the desired shape. One major difference between that, as I said, that the depth of the stretch is less than the blank diameter, then you call it as stamping. Otherwise, it is the same, process is same, machine will be the same, only the terminology is different. Now, when you wanted some specific with a high precision and accuracy, some specific shapes and other things if you wanted, then hydroforming is extensively used, and this is extensively used for automobile body parts, where you get a very good surface finish and the production rate is much higher, and the defect or rejection in the process is very minimum in this case. Once you standardize it for a particular component, the rejection is almost nil. That is one biggest advantage with this. So, hydroforming, it is nothing but you are going to have a hydrostatic pressure on the sheet metal. Okay. So, equally in all directions you are going to have, wherever it is going to stretch and other things. So, in the process you will get a uniform section thickness. So, that is what this hydroforming. So, the process is very simple. You have a control fluid pressure forming chamber. So, this will be a flexible die member, something like it may be synthetic rubber. Okay. This is made of synthetic rubber. This flexible die member is a synthetic rubber, and there is a wear pad also, so that this rubber also will not get worn off. So, those type things are there, and your blank is kept on a die, and maybe inside a blank holder ring. Inside the blank holder ring you are keeping it, and then the whole arrangement, this whole arrangement, it will move up and then press against this the top part, okay, about this fluid pressure forming chamber. So, you remember that here there is fluid. So, this is rubber. So, that also will act like a hydrostatic type of stress. So, you can get, it is very flexible, and then when once it comes and touches here, this punch moves upward. This is the punch pushes upward. So, now once it comes and presses here, what will happen is that you will pressurize this fluid chamber, okay. With a high pressure you are filling it, it will be under high pressure, and now what happens is that this punch, you will see that the punch shape is there. So, whatever shape you wanted, it is that shape, the punch will have that similar shape here. So, this punch moves up, and when it is moving, see this flexible pad is there, which is rubber, that will elongate, no problem, but the fluid pressure which is there, it will exert a hydrostatic stress in this equal in all directions. So, you will find that whatever is happening, the thickness remains almost the same, and once that shape has come, then you just retract the punch backward, and then you will get this finished part, and lower it, you get the finished part, you take it. The biggest advantage in this is the thickness remains almost the same in this case, because it is uniformly deforming throughout the part. So, that is one thing. Second, the defects are reduced, and consistency in the quality is also maintained in this. Drawback is that this rubber padding, it may get worn off very fast, you may have to remove. So, that will increase your cost of the component, because rubber material itself is costly. So, that is another. Another simple method using a simple press and other thing is that, okay, you have this a form block is there on which whatever shape you want, and the metal blank is kept there, it is pressed against a rubber pad itself. There is no hydraulic pressure here. This is a retainer on which the rubber pad is there, you just press it. This is for simple shapes and other things, this works out, okay. Because this because of the rubber pad itself, that itself will act as a give a sort of to some extent a hydrostatic stresses it will give, and due to that you can get the shape. So, on the foam block, whatever the form shape is there, that you will get it. So, that is what is hydroforming. So, hydroforming is that way a very convenient thing. Only thing, initial investment may be high, but compared to the production rate, that will be balanced off. The advantages of hydroforming are inexpensive tooling cost and reduced setup time. This is one biggest advantage. Once you fix it, then you can start making in large number. So, that is the inexpensive tooling cost, but machine cost is high. It is not very high also, but the tooling costs are not high, okay. It is very cheap, and due to that, not only that, the setup time is also very much reduced. It is a very simple thing only to fix it. There is nothing like exactly arranging these parts and matching and other things. So, that is not coming into picture. Then reduce the development cost. So, once you have the machine, then any type of component can be like you can have a variety of components made into that. Not any shape cannot be made, but you can have a variety of shapes. So, component also, for that the development cost will not be very high. Then the shock lines, draw mark, wrinkling and tearing associated with the matched die forming, these are all eliminated. These are not going to happen because of the hydrostatic stress. Okay. Wrinkling will not be there, draw mark will not be there, shock lines will not be there, and maybe some tearing also because of the hydrostatic pressure. So, that way the tearing also may be eliminated. The thinning of the material, because it is a hydrostatic stress and it is deforming uniformly in all directions, whatever thinning is taking place, it is uniform. So, localized thinning is not there. Okay, so that is minimized, that is one advantage. And low work hardening, then multiple conventional draw operations can be replaced by one cycle in a hydroforming press. This is the biggest advantage. So, instead of 2-3 operations, this you can do it in a single operation just by your pressurizing the chamber, pressure chamber and other thing, and then having a proper shape on the punch and other thing. So, that is one biggest advantage with this thing. And this is ideal thing for complex and blank complex shape and irregular contour. This is the answer to that. Other shape, it becomes very difficult. By other methods it may not be possible, but by hydroforming you can have that in a complex shape also, and irregular contour also you can have it. And the materials and the blank thickness specification can be optimized to achieve cost saving. So, these are some of the advantages. So, next method is your tube forming. In the tube forming, say you have tube and then you have to give it different shapes. Maybe you may have to bend it, you may have to say enlarge the one end, you may have to reduce the diameter at one end of this pipe. These are all done by tube forming operations. Okay. So, you can see that, say here there is a particular dimension, this was a pipe, and then or a tube was there, here the dimension is different, here dimension is different. So, you may get it was a straight pipe, now you are getting this type of shapes. But remember, when you are bending the tube, there is every chance that it may collapse at the bend. So, you have to do it effectively, so that it is uniformly bent without collapsing. Okay. If it is collapsing, it will not serve the purpose, and your efficiency of the performance of the component or the machine will be affected. So, you do not want that. So, in this case, see, instead of just bending, say bending may be done between a pipe bender. Okay. The tube blank will be placed in a pipe bender and clamped between two dies, and then a mechanical by means of mechanical means you are pushing it, and subjected to force, the tube blank move against the die and come to the required shape and other thing. This is what is generally done. And but a tube, when you are just bending, it may collapse, as I said, it may collapse. So, you may have to do something. Some people fill it up with the sand and then bend it so that it is cylindrical in shape itself, or some people may just fill it up with water and refrigeration, they do it so that it becomes to ice, and then both the ends are closed and you bend it so that this circular cross section is maintained. So, like that, depending upon those people who are using it, they will come out with their own ways and means of bending without this collapsing of the tube at the bend. Now, in case if you wanted to expand the tube end, say like here now from the tube you wanted to expand this, then use a flaring tool. So, you just a flaring tool, you insert it and rotate it, and then finally get that shape, you press it into that and then you get that shape. So, that is a flaring tool. But if you wanted the diameter to be reduced, then you press it through a sinking die. Okay. Die sinking, so through that you just pull it and then get it. So, there also you can rotate and get that. In that case the metal, it will thin, whereas in this case of flaring tool, when you are using to increase the diameter, the side wall will get thinned off, whereas in the sinking, using the sinking die, you will find that it may be slightly increased only. So, this tube bending, so lot of shapes are used in tube bending. Another method is the coining. See, coining is like how you make a coin. Okay. So, metallic coins are there in almost every country, there are coins. We have 10 rupee coin, 5 rupee coin, 1 rupee coin, 2 rupee coins and other things are there. These are done by coining process. So, what you do is that you are going to have a piece which is kept here, the work piece is kept here, and then between an upper die and a lower die, you just press it. So, depending upon what is the shape here, what are the feature you wanted here on the coin, So, the reverse of that will be, reverse impression will be there on the on your die and punch. Okay, like if you take a coin, on one side it is head and the other is tail, you call it as, no. So, on one side that impression, the reverse impression, we can say that, like it's not, we cannot call it as a mirror image, but the what is that, male and female joint type thing. So, that impression should be there on the upper die, and similarly on the other side whatever will be there, you wanted it on the lower die, and then the metal is there, and then you are pressing it. When you are pressing it, some plastic deformation takes place and metal will flow into this, all these contours, and then fill it up. Okay? And then finally it is taken and then it is what is that, shade. Okay? Blanking is done, sorry. Okay? And this coining is always a cold working process. Okay? And these are used for making coins and medals and many of these type things. The pressure which is acting on this during the coining will be very high. Okay? It may be of the order of 1600 or 1000 megapascal to get the desired impression on that. You may have to apply a higher pressure on this. Another method is ironing. So, ironing is a continuous process which is used to thin the side walls, and maybe you may get with a concomitant increase in the depth of the cup. So, that is the thing. These are all sectional views which are shown. So, here you will keep the blank here, and the punch you will through with the help of the punch you are just moving it, and then so maybe depending upon the clearance between the punch and the die, your thickness will get reduced. Okay. So, that is the main method of ironing. So, at the start it will be like this. Maybe when you see that on this die itself, there is initially it may be like this, but somewhere below that you will find the die shape is like that, there is provision for thinning. So, in that case metal will flow along here, and so till the complete punch traverses downwards, the full extent if it is there, till that time it will just keep on. So, but you have to be very careful, otherwise sometimes still the full metal may not be enough. So, that punch stroke adjustment you have to do it properly. So, in this case if you look at it, you see that here okay, it is like a deep drawing operation, but when it comes here there is a thinning which is taking place. The side walls gets thinner. So, but you can have this arrangement by using a series of dies, one after the other you can do it. So, that in one stroke itself you can get a large reduction from the initial thickness to a final thickness. In one stroke itself we can just arrange this die. Next part there is a die here, when it moves here where the still clearance is less and other things. So, that is one advantage. So, more than one half the thickness can be reduced to, so almost half, that is 50% reduction you can have it in a single stroke by this one. So, by means of ironing. So, that also is a extensively used process. Another method is the spinning operation. See, one is simple metal spinning and another is the shear spinning. So, you have a mandrel, say like this mandrel is here, and then this is held on a lathe, and by means of your tail stroke and head stroke, now you just keep it on this, and this is the mandrel and your workpiece is, this is the workpiece. Okay. This is your workpiece, and then it is rotated, and a tool is allowed to move along in this direction. Okay. So, you will get this particular shape. So, it will get the shape. So, you will get a cup type thing. So, inside will be corresponding to outside of this mandrel. So, that is what you are doing. So, that is a simple spinning operation. So, it is a process in which a disc or metal tube is rotated at high speed till it attains axial symmetry, and then by means of a roller tool you are just allowing to deform it and then get this particular shape. Whereas, in shear spinning, not only that shape is obtained, you may the clearance between this roller and this your mandrel is very less. So, that you may have to there will be a thinning effect in this. So, lot of plastic deformation takes place by means of the roller tool, its thickness gets reduced. So, that is the thing. and till this part when it comes here, no, you are getting this shape. This is the intermediate stage, this is the starting stage, this is the intermediate stage and final shape. So, initially your blank thickness was this much, but when you are getting the side wall thickness is much less than that. So, that is what is called as shear spinning. So, here plastic deformation, shear spinning, plastic deformation is taking place, and you can have a correlation between what is this angle and what is the thickness you are going to get it. So, that we will discuss about it later. So, by shear spinning also we can have it. Now, this roll forming is there, you want a particular shape and on a continuous long sheet, if it is rare, you wanted to shape. You have a simple plain sheet like this, and maybe your final shape is something like this if you want. It is not that only one, you can have multiple also. You see that it is passed through a series of rolls. See, this is the first roll where it is plain and other things, and the second roll comes now, you see the size of the roller is different. So, there is going to be a small amount of deformation. When it comes to the third one, okay, the sheet metal get deformed in this form, in this particular shape, and the fourth one you are getting this shape, and finally, the fifth one also you are going to get it. So, by a sequence of passage through by the passing through a series of rolls with the different contours, finally you get the final shape what you want, and if that is on a single sheet, on a continuous sheet, then you go for this roll forming. So, because it is passed through between pairs of rolls. Okay. So, like each stage there is some amount of deformation to get. So, that straight in one go you are not going to get the final shape. Okay. So, in a progressive way you are going to change the shape and finally you get it. The assembly line is there, no mass production can be done easily. Okay. So, that is one thing with roll forming. Another is the superplastic forming. Only drawback with the superplastic forming is that it is a slow process. Okay. It takes some time, but you can get deep recessed parts. Say for example, if you want that shell for your granite and other things, okay, grenade and other things, when you wanted, then this bomb, what is that, that casing. Okay. So, all those things you can have. For that the superplastic forming is known. See, superplastic forming is that when you are deforming the material, there is no necking taking place. The material exhibits superplasticity when you say that there is no necking with the string. When in our tensile strength, after reaching the ultimate tensile strength, then you will see that the load drops. That is because of the necking takes place at localized region, which we have mentioned in our first class or second class, first lecture or second lecture of the module 1. So, that so under certain specific conditions, any material, most of the materials will exhibit superplastic deformation. So, once it exhibits superplastic deformation, your percentage elongation can go up to say maybe 600 or 1000 or 2000 percentage. Okay. So, you start with a very small piece and then you are able to elongate into a very fine rod. So, simple example is you take a glass rod, heat it under a just heat it, and when the temperature crosses around 700, 800, you can just pull it like a, and then it gets reduced into a very fine form. So, a small area, so it will get extended to say more than 1000 percentage. Okay. So, that is what is called as superplasticity, and the process of deforming under superplastic condition to get a shape where you can have a large amount of strain. So, that is called as superplastic forming. And by this process you can get very thin walled component to a very high accuracy and good surface finish, all is possible by this. Okay. Advantage of this process is the low strength tool, and then complex shapes can be formed, and low tooling cost and high rate of production. Rate of production is not that very high. Okay. But so other things are fine. You can get a very complex shape with very high intricate shapes, you can get it. That is one advantage, and cost is not very high. The principle behind this, see, when you wanted a material to have superplastic deformation, the general metallurgical reasons which they give is that it should have very fine grain size, something between 5 to 10 or 5 to 15 micrometer diameter, not higher than that, very fine. The structure should contain two phases. The continuous phase should be ductile and the discontinuous phase should be brittle, and this should be uniformly distributed. These are the conditions which is difficult, but not impossible. Okay. So, and in that case, and then you are deforming it under very slow strain rate. Okay. So, strain rate is very low, that is why it takes lot of time in this process. So, what you do is that you just have a superplastic material is kept here first. Okay. This figure is showing at the end, and then there is a seal bead which is there. So, that will just separate out from the region above this sheet and below that sheet. It will be completely isolated. Okay. So, for that you need to have a seal bead and other things, and then the whole setup, if you wanted to do it at a higher temperature, you keep it at a higher temperature, and when the temperature is reached, so entire thing, that temperature, particular temperature, once it is reached, then you just introduce some forming gas into this top chamber. So, what happens at that high temperature, and this will be generally be done at a low strain rate. So, this will just keep on moving like this. Okay. And once it, see, because necking is not taking place, so fracture will not take place. And but only thing is that this has to be carried out at that particular conditions. Okay. But the biggest advantage is that if a material, say for example, titanium, aluminum, vanadium is a extensively used superplastic material, and it is used for space application and defense applications in a big way. So, that sheet, when you are keeping it and then you are going to apply this pressure at a very slow rate. Okay. So, but that sheet should have all these conditions, that microstructure it should satisfy, two phase, and one should be, the brittle one should be discontinuous. Okay. And then it should be deformed at that particular strain rate, which is generally very slow strain rate, that is of the order of 10 to the power minus 3 per second and other things, all those things. So, here once you seal it, you pass this gas at that particular temperature, and so it exerts the pressure on this. So, that will allow this metal to deform superplastically. So, it will not result in necking, it will just deform, and then okay, it will come and touch this formed die on this walls and then stop it. Okay. So, that is how this it is done, but this strain rate is very very low. So, it takes a lot of time, but you will get it with a very good surface finish and very close dimensional accuracy. Now, coming to this other parts, like when you go for this for the analysis, we will have to think about various points, like okay, what are the properties the material should have. It is not that okay, you cannot take a brittle material and do a sheet metal operation, it is not possible, it will just crack. So, material should be ductile. So, you need to have certain knowledge about this material properties. So, this part was mentioned earlier, the very important criteria for selecting a material depends upon its functionality, that is there. And in case of sheet metal forming, the most important criteria is the formability. That means, the relative ease with which we can deform the material, that is called as the formability. So, you should have an idea about the formability of the workpiece material which you are going to deform it, that is very essential. And once you have this formability assessment, once it has been done, this helps in describing the behavior of the sheet during forming. So, under what conditions it will deform. So, and whether you can go deform the material up to this particular limit, or it can go to infinitely, or what is the limit beyond which if you try to deform, it will result in say cracks formation, and then subsequently it will fail. Okay. So, you should have an idea what is the limit at which, and if you still wanted to go further, what you will do. So, for that this formability assessment, if it is there, that is very good. And you will see that sheet metal forming involves both elastic and plastic deformation. So, this is a typical load extension curve which we have done, and from this we can get your stress strain curve also, and then if you know the dimensions, then you can find out the true stress true strain curves and other things. Now, at the onset, initially when you load it, it will deform, but after certain time it will start deforming, and that load at which it will start deforming is called as the yield point. Okay. So, at the onset of this yielding, the plastic deformation starts, and from there till it reaches your ultimate tensile strength, the material undergoes work hardening. Initial work hardening will be higher, but when you move towards the later stage with the increase in the extension, the work hardening rate will decrease, and finally it will saturate out. Okay. So, during the strain hardening, the strength and hardness, that means from this region, from yield point to your ultimate tensile strength, the strength and the hardness of the material increases along with the increase as the plastic deformation increases. So, that is one thing. So, maybe after this deformation, you may get a material having higher strength and hardness. If that is required, we can use it. If that hardness and strength at that region is not required, we can give a heat treatment, annealing heat treatment, so that it will be nullified. Okay. So, but one term which we have not discussed so far compared to bulk deformation, we could have discussed there also, but purposefully I did not discuss it there. So that we can go into depth here, that is the anisotropy of the material. Any sheet metal, especially if they have been cold deformed, you can easily find out in which direction this has deformed, because when you look at the light, reflection of the light, we can make it out in which direction it was deformed. Okay. So, that is one floor test to find out which is the direction at which the sheet was rolled. Okay. So, that is there. So, all these materials, you will see that its properties of this metallic material depends upon the microstructure. And in microstructure, what is that? What are the phases? What is the grain size of these phases? And what is their orientation? Because almost all sheet metal comes in the after secondary processing, maybe by rolling or forging or drawing or whatever it be, it comes after the secondary processing operation. So, that large amount of strain has been there. In this case, what happens is that grain size with the extent of deformation which you have imparted onto that, the grain size will get reduced. If the deformation was less, grain size will be large, but if you have given extensively deformed it, grain size will be less. But at the same time, if you have given after this one, if you have given a heat treatment, then it may become very soft also. So, all these things are possible. But ultimately, when you look at the structure, you will find that what decides the properties of the material below the equiviscosity temperature, that is the grain size and the grain orientation. So, higher the deformation which you have given, the lower, finer will be the grain size. Finer means smaller size. Okay. Coarser grain means a bigger size. That is what. So, finer will be the grains. And you will find that the grains are oriented along certain directions. A phenomena which people abundantly use now is the texture. So, most of the case after large number of deformation, you will find that a particular crystallographic, the crystallographic planes of one grain, it is arranged in a particular direction, along a particular direction. Similarly, you will find for most of the grains, it is arranged in that particular direction, along that particular direction. So, that is called as the preferred orientation. After this extensive deformation, the grains will orient it in a particular fashion, in a particular direction, which you call it as preferred orientation. Okay. So, the grain size and grain orientation, so they are influenced by the extent of direction of the secondary processing, the extent and the direction of secondary processing. And based on that only your properties will change. So, due to the orientation difference, the properties of the sheet metal vary along different directions, because if the grains are elongated along one direction, and then in other direction if you apply, maybe the properties will be poor, whereas when you have applied along one direction, along that direction properties, mechanical properties will be better. So, that is one thing. The phenomena of having different properties along different directions. So, suppose I have a sheet like this, and this was the rolled direction. If I just take a sample like this and then study the properties, but if I take at this 90 degree to this and then study the mechanical property, here no grain orientation was like this. So, here the transverse properties will be very poor. Similarly, here it will be the maximum. Similarly, if you are having something like this orientation like this, then it may be intermediate between these two. So, in this case, when you look the properties along this direction and the properties along this direction and the properties along these directions, these are different. So, if they are different, then you say that the material exhibits anisotropy. Okay. So, in a single sheet, from that you cut your tensile samples along different directions and then study, you will find that they are not same. But along the same direction, if you just take it and conduct a large number of tests along a particular direction, then you will find that it is a reliable result. If it is larger than 5 or 10, then you consider it as a reliable result, and take the statistical values and to find out these properties. But if they are different, then you call it as this is exhibiting anisotropy. So, anisotropy in sheet metals are quantified by this term R value. Let us see what is this R value. The R value of a metal sheet is defined as the ratio of width strain to thickness strain, in whichever direction you are taking. But along the axis of the tensile stress, if that is taken as a length, then the width and thickness is there. So, the strain along the width and the strain along the thickness, the ratio between these two is called as the R value. That means, the strain along the width strain is this, and this is the thickness strain. So, R value, when you just do that, is EW by ET. So, that is equal to, say, you can say log W by W0 by log thickness T by T0. In this ratio, when you take it, what is that value you are going to get, it is called as the R value. Now, this R value depends upon different directions also. As I said, maybe you are just cutting the sample along the direction of rolling, another you are cutting along the direction transverse to the direction of rolling, another you are cutting a sample from which is equally inclined to both this length and the width direction. So, in those cases, your properties will be different. So, when it is along the direction of rolling, then you call it as R0. When it is transverse to that, then you call it as R90, and if it is taken at 45 degree inclined to this direction of rolling, then you call it as R45. So, that is the only difference. So, this R0, R45 and R90 represent rolling, diagonal and transverse directions respectively. If these values are not identical for a material, then the material exhibits planar anisotropy. So, what is this planar anisotropy? Let us see. And if the measured R value is not unity, if it is not unity, it depicts a difference in plane between the in plane and through thickness properties of the material. So, if it is not unity, because the strain along the width and the strain along the thickness, it is different. So, you will find that there is a difference between the in plane and through thickness properties of the material, and which can be evaluated by the term normal plastic anisotropy. The normal plastic anisotropy R bar is defined as 1/4 of sum of R0 plus 2 R45 plus R90. This we can easily get it from your matrix tensor, this one now you can easily get it into this. So, this is much easier. So, and then that divided by 4. So, that is what you call as normal plastic anisotropy. Another thing which you have to consider is the strain rate sensitivity M. See, we have earlier discussed the Holomon equation between the stress and strain at room temperature, but when you go to a higher temperature, it is entirely a different thing. So, where K is the sigma is equal to K epsilon raised to n, where K is the strength coefficient and n is the strain hardening exponent. Now, in this case, you will find that lower the yield strength, if the material is having lower yield strength, then it is susceptible to rate of deformation, which indicates it depends upon the speed at which the experiment is performed. So, this is the case at a particular speed, but if you are doing it at a very high speed, then you will find that there is a difference in the flow stress. So, at a higher strain rate when you are doing, you may find you will end up with a higher flow stress. Okay, so, that is there, and then that will be different for each material. So, we can say generalized relationship taking into account the strain rate effect, you can write in this form: sigma is equal to K into epsilon raised to n into epsilon dot raised to n, where epsilon dot is the true strain rate and M is the strain rate sensitivity of the material. Okay. So, that way you can find out this flow stress. Now, there will be abrupt change in the load upon sudden change in closed velocity, that also will be there. It is evident from the figure that the abrupt change in velocity causes sudden change in the load, but this we cannot help it actually. So, strain rate is epsilon dot, that is equal to V by L, where V is the velocity of the material, a constant velocity, or maybe velocity depending upon say your workpiece material. Okay. And L is the length of parallel reduced section of the sample. So, by that relationship we can get this strain rate. Now, the strain rate sensitivity M is determined using the data obtained from a rate jump test, which we have discussed in our initial lectures. I think second or third lecture we have discussed about you do it at a particular strain rate. So, epsilon dot 1 and this is epsilon dot 2. So, when this is done, so epsilon dot 2 is greater than epsilon dot 1. In that case, you will find that maybe at this point it was epsilon dot 1, but suddenly you change to a strain rate of epsilon dot 2. So, there is a difference in the load. So, from here to here you will find that there is a big difference in the load. So, that load you take it and then you can just substitute here in this equation, the derivation we have earlier mentioned also. M is equal to log P 1 by P 2, P is the load and by log V 1 by V 2, that is the velocity, this one. This is the it will give you a strain rate sensitivity index. Okay. So, I think with this I will stop today.